Good day, everyone, and welcome to today's webinar. Before we get started, we would like to review a couple of items. We welcome your questions during today's webinar. Please use the Q&A button located at the bottom of the viewing screen to ask any questions you have at any time during the broadcast. We will answer your questions at the end of the presentation. Also, today's webinar is being recorded. A link to the recording and the slides will be sent via email following the event. And with that, I'll begin my presentation. Hi, I'm Eliran Sinvani and I'm working in Scylla's core as a team leader. My team and I are working on developing cool new features for ScyllaDB and improving some of the old ones. Our team recent work was the implementation of materialized views and secondary indexes, and of course, workload prioritization, which I'm going to talk about today. A little about ScyllaDB. We are behind Scylla, the real-time big data database. Scylla is a drop-in replacement for Cassandra, but with 10 times the performance and low tail latency. We are available on the cloud and on-prem with both open source and enterprise editions. If you haven't already, I encourage you to try Scylla. We are going to first establish some basic concept, then we will define the problem that workload prioritization is trying to solve. We will talk about how did we implement it, show some of our own experience results, and finally, we will share a real use case where workload prioritization saved the day. So workload prioritization is all about dealing with different loads on the same cluster. Before we can define what workload prioritization is, we need to define what are a workload's key characteristics. So the main characteristics for a workload are latency. This is the time it takes to the server to answer on a query measured in some time unit, usually seconds or milliseconds. There are many variations of measuring latency, but it is not that important for our discussion. What is important is that latency, although very good in ScyllaDB already, can't be much reduced. And we will try to explain why later with an analogy. Throughput is the amount of data or operations processed by the server per time unit. This can be increased by expanding the cluster and adding hardware and nodes to it. Those make up two common workload types. OLTP stands for online transaction processing. This type of load is typically generated by individuals or by applications that needs to do a large number of unrelated queries. The most important thing about this type of traffic is that it's usually latency sensitive. Good example is user operations on websites. OLAP, on the other hand, stands for online analytical processing. This load is typically generated by a single client and involve consuming large amounts of data by running relatively small amount of queries, or alternatively, large amount of queries where the individual per query latency doesn't matter as much as the amount of queries processed per second. This is typically some kind of an analysis on the existing data, which in turn often generated by OLTP operations. One justifiably may ask, okay, so why can I simply do both? The main problem is that those workloads conflicts. Generally, the higher the throughput, the higher the latency. We'll try to use an analogy. Let's say you own a restaurant. If you want to be successful, assuming that you already have great menu and recipes, you would like two things to exist. One, on the customer experience side, which is the analogy to OLTP, you would like the customer to have a good experience and that it will get his order fairly quickly. That is, you would like a good latency for individual orders. On the business side, which represents OLAP, you would like to sell as much meals as you possibly can per hour. This is throughput, to increase profit and to make use of all of the cooking stations you have built. So most of the time, you can pull this off. Customers get in, sit down and order sporadically and get their meal after a short while, since there is always an available cooking station to start preparing their order immediately. The problem starts during lunch, which you certainly want to take advantage of because this is your chance to increase sales. Let's say you get initiative and even open a website for lunch orders. So everyone order at once, and now you can no longer guarantee that client's order starts to get prepared just as the orders. since all of the chefs are busy. So this poor customer and every other that enters the restaurant after him have to wait for all of the orders that came before him to complete. Because there are more than the kitchen can handle. Or in other words, the customer experiences an increased latency. So does the online customers, but they don't care that much since they are going back to their business until the delivery comes. The aforementioned customer is likely not to come back to a restaurant, but you increase your throughput since your cooking stations always prepared something, so you maximize your profit. Another thing to notice is that the latency has a limit that it can reach. A boiled egg will never take less than 10 minutes to be prepared. But on the other hand, you can always build more cooking stations and hire more chefs, and by that increase your throughput and make more boiled eggs at every given time. Although you are likely to go bankrupt if you build too much of them. This conflict is usually hard to solve in the database world, and the common main concern is that OLAP, those lunch orders, will impact OLTP, the individual customers that come into the restaurant. Even before workload prioritization, there were some quite simple solutions for this problem. The first one is just have a data center per workload. This is the most widely used solution. The other is to run OLAP only on the non-busy periods. Both has their problems. The former can be pretty expensive and the latter is logistically hard to achieve. There are some additional creative solutions, but usually they are too proprietary or complicated to implement. One can argue that maybe it's not a problem at all. So maybe we can just run both workloads on the same cluster and all will be well. When working on the blog, we actually did try to run OLAP and OLTP together. It wasn't pretty, especially compared to the alternatives. Here's what we got. What can be seen here is that as soon as OLAP kicks in, the latency is severely impacted for both workloads. The key here is for both workloads. So let's have a look on the two most common solutions to the problem. We'll start by multi-DC one. So let's say we set up two data centers. We try to save some money by downsizing the OLAP cluster relatively to the OLTP a little bit, assuming that we even can. It's not all bad. It is a good setup for most cases since OLAP is often only a read workload. So the synchronization will happen only in one direction, from OLTP towards the OLAP data center. The OLTP cluster is underloaded. This is obvious since we needed to be ready to serve new requests as soon as they come in order to achieve low latency. The OLAP server, on the other hand, is very busy, but only for short periods or alternatively with long pauses. Analytical operations are done only once in a while, when enough new data was generated. So actually, most of the time we're just paying money so the OLAP DC can stay in sync with the primary DC and for the OLTP to be ready to receive more requests. So let's look into time division maybe. This is already better. We are only using one data center. As for the OLTP load, that doesn't change, same occupancy percentage. But until now, for less money, so it seems we're on the right path. We will pick a time where OLTP is at the minimum, let's say 30 or 40%, and start the OLAP load. Now we have a problem. Both loads together needs more than 100% of the cluster resources. What will actually happen is that OLTP requests will start to get increased latency, and it will keep increasing as a dependency of the OLAP load. It can eventually time out, since OLTP, as we said, is usually latency sensitive. To put this in numbers, this is an analysis done by Glober that show the amount of potential money waste. This emphasizes why it is important to utilize your cluster, if you can. It shows that almost half of the money you pay just goes to waste and you don't actually use your cluster. So this is where workload prioritization comes in. Workload prioritization is an enterprise-only feature. The essence of workload prioritization is to resolve this conflict by prioritizing. This means that we can choose in advance which load will get resources when there is not enough of them. We can theorize and make assumptions, but our first question should be, does it actually work? So, as you can see in the spoiler, it does work. This graph is taken from the same experiment from several slides ago that shows the impact of OLAP on OLTP's latency with a slight difference. It utilizes workload prioritization. The key is to notice that OLTP is getting better latencies than OLAP, and they don't just converge as before. Let's try to look into the core of the solution and explain how and why it works. In the past few years, we have been working to tweak Scylla's resource management for an entirely different reason. We wanted to actively balance between our background work and foreground work. We decided to use schedulers. Those schedulers are at the core of the solution for balancing between our background and foreground tasks, and also, in turn, the core of our workload prioritization solution. Our schedulers work with a single configuration parameter, shares. The concept of shares is very simple. Shares are used to bias the fairness of the scheduler. Shares can be thought of a number that determine the percentage of ownership of the resource relative to others, just like real stock market shares. If you would like a fair split of resources, just use the same amount of shares. Here you can see that the blue and red workloads, each one gets its slice, and it's an equal slice because they both have the same shares. On the other hand, if you would like to bias the scheduler in favor of one of your loads, in this example, the blue one, just reduce the less preferred workload shares. So we reduced it to 50, half of the shares that the blue one held. And we can see that the blue one gets twice the time slices or the resource slices as the red one. Alternatively, you can increase the preferred one. So you give 200 shares to the blue one and 100 shares to the red one, and you get the same results. The reason is that shares are only relative. The actual number doesn't matter by itself. If you only have one load or one consumer, it will not be that important how much shares it really gets, because it will get all of the resource and will get to it. Shares are the only configuration knob for schedulers. It makes the configuration quite simple and keeps the focus on the task that needs to be tweaked. This helps to keep the system always utilized. If a task needs a resource and it is available, it will simply get access to it. On the other hand, when there is a conflict, the task that holds most shares will get more of the resource. Scheduler opts for a ratio of resource usage between the shareholders. This means that starvation will never happen, even for the task that holds the lowest amount of shares, as the ratio is maintained constantly. The number of shares can be changed real time. This gives opportunity to Scylla controllers that we will soon talk about briefly, to balance the background and foreground work in Scylla. When you set shares, you actually set implicitly the minimum amount of resource that a task will get, which is the percentage of shares of the task owned out of all shares in the system. It is not accurate to the digit, but it is guaranteed that the scheduler will adjust the trend to converge to this. Another nice point about this is that you don't limit the maximum. So in other words, a certain service can be impacted, but it will never get less than its implicit minimum for too long, and definitely not permanently. And they will not be starved for nothing. If the resource is available, they will just get access to it. For solving our first problem of background vs foreground tasks, we took advantage of the fact that shares can be changed in real time. To create feedback loops, we call those feedback loops controllers. Those controllers use some metrics of the system to adjust shares in order to tip the balance in favor of certain tasks. So the controllers use schedulers to converge to a stable state in the system by increasing or decreasing the amount of shares a certain background task has. Here we can see how the compaction controller changes ratio between throughput and compaction automatically. It looks at parameters like how fast is the compaction backlog increases to decide when it becomes more important to give it more resources than the foreground tasks. There were other solutions that we considered. The major one is to just limit the throughput with absolute numbers. This solution is actually used by some of other databases. For example, set hard limit on compaction to never use more than a certain disk bandwidth. But we found the controller solution superior to this method for the following reasons. Firstly, it gives better system utilization. It doesn't limit anything as long as there are enough resources to go around. It's easier to tweak. Absolute numbers change with load size, hardware types. If you get another hard drive, for example, you might need to tweak all caps on I/O bandwidth that you previously set. The third reason is that database loads are dynamic. It is hard to predict the ratio or the bandwidth between background and foreground loads and what each of them will need. So schedulers are also the core of workload prioritization. We simply expose to the user a way to give every workload its own shares of the system resources. We use those shares to configure the CPU and I/O scheduler. In the future, we might tweak others, such as memory and network schedulers. Using the benefits of using schedulers, they are easy to configure. A single configuration parameter to control the behavior. They can be dynamically adjustable, allowing trial and error. The utilization is not harmed since they only limit access to resources when there is a conflict, meaning a user can set them without the system change its behavior when it's not overloaded. Of course, it will change its behavior, but for the better when it is overloaded. And the most important thing, it solves our problem by limiting the impact between different loads. Schedulers gives the appearance of parallel queues, but it's not enough. Wherever there is a single queue, there can be a head of line blocking, or this queue, if this queue has a set maximal size, a starvation of a high priority task can happen by a low priority task just filling up this queue. The more of this serialization point we parallelize, we will have less cross interference between two different loads. This part still has some work to be done, but it's already in a good shape and it will only get better. The last challenge is to keep track of the operations and know the priority. We need to make sure that those priorities propagate to all of the side effects, such as background read and writes or view writes, and also propagates through network boundary, for example, reading information from a replica. Here too, we keep improving, and as we do, a better isolation will be achieved between workloads. So we will quickly go over the two main use cases for workload prioritization. We'll show how easy it is to configure them and show some more test results. Configuring workload prioritization is a 3 short steps process. First, we make all users that generate the same workload. We create for them a joined role and attach it to them. Then we create a service level for the workload and set its shares. As I said, the only configuration parameters is shares. Then we attach the service level to the user's joined role. From that moment on, they are collectively granted the shares and will participate in workload prioritization. Now we will take a look how does it actually achieved using CQL commands. So those are the corresponding CQL commands. As you can see, all that it takes is 4 CQL commands and you are all set. The first two create the role and grant it to some users. The second is create service level and sets its shares. And the three connects between the two, which meaning attaching the service level to the role. Let's go over to general use cases where workload prioritization is a good fit. The first one is our OLTP vs OLAP problem. We'll try to make it happen on a single cluster. Here is a graph that shows that what happens when we use this configuration to keep the ops of the OLTP load relatively stable when OLAP kicks in. When OLAP kicks in, and OLAP can get whatever that is left. So as you can see here, the number of ops is fairly stable, and OLAP, although it only gets 10 shares, is not starved. On the contrary, it gets more ops per second because it demands it. And as long as the system has the resources to give it to him, they give it to him until they cap him when the load is at 100%, not more. So the actual workload prioritization is generally facilitate resource division between several loads. There are a lot of effects that can be achieved, but one of them is something like this. This is a more general example. We have 3 workloads that we want to balance between. It can be seen that the client observed latency is lower as the shares number is higher relatively to the other load. So again, we cannot stress enough that shares are relative. And another thing is latency. Low latency is good, high throughput is good. So this is a different graph for the same configuration. Here we can see the throughput. And we can see it's higher as the number of shares is higher relatively for the other loads. So, of course, load 3 will get most of the throughput, most of the operations per second. And the workload 1 will get less. Now we'll share with you one of our customers' use case where workload prioritization was actually used to solve a problem. So what you see here is taken from status report by our field engineering team from mid-June. The situation analysis as explained by our field engineering manager, Glover Costa, is the customer is an ad tech shop that runs a heavy read load against the cluster. The cluster generally operates at 70% capacity and serves the queries just fine. However, every 10 minutes, many clients would fire heavy allow filtering queries that essentially scan the entire database and that would push the nodes over the limit. So the scanning means that they try to get a lot of data, a lot of throughput, and those peaks are very common to OLAP traffic. So we have a classic case of OLTP vs OLAP, actually. In the graph, you can see those peaks, those every 8-minute peaks, which are so common to OLAP. So after analyzing the traffic, our experienced field engineers root caused it to conflicting workloads, of course. The burst of scan requests increased the latency for all of the pending requests in the cluster, resulting in timeouts. Actually, it was even a little bit worse because when the OLTP load got the timeouts, it just resent the old queries. So queries kept build up in the server until it just crashed. So it is obvious that the bursty client is less concerned about individual latencies and was more about throughput. So our engineers had to let him have all of the remaining bandwidth, but not more. They did it by using workload prioritization. Those 2 sentences are taken from an email response by Glover to the question if workload prioritization worked for the customer or not. So it is easy to get, it is easy to analyze because they had timeouts and now they don't. So workload prioritization did an adequate job in isolating the loads. One key to take from this is that the change to the client applications and clients was as minimal as logging in with a different username. And in a lot of cases, even this is not necessary, since the clients already have different users' names for reasons other than workload prioritization. So I'll just summarize some key points for workload prioritization. For conclusion, I will go through some highlights and pitfalls regarding workload prioritization and Scylla scheduling. So the first thing is that authenticator must be set for the feature to work. We have to be able to identify the origin of the load in order to prioritize. If we don't know the username, so we don't know who is behind the load. Every user that doesn't get an explicit service level is automatically assigned the default service level. It is configurable, but you should take into account that changing the configuration will affect all users that weren't assigned a specific service level. So if this is the majority of your cluster, you have to consider it very carefully. Shares are relative. The absolute value doesn't matter, only the amount of shares relative to other shareholders. We only guarantee trend and not absolute throughput or latency. Actually, it's not only relative to the shareholders, but relative to the shareholders that also wants to use the resource at the same time the task we discussed does. Workload prioritization only applies for when there is a resource conflict, which is an advantage since when there isn't a conflict, the system can be fully utilized. Workload prioritization does not guarantee good performance on its own, nor does it guarantee absolute throughput or latency. This should be achieved by other means like correctly sizing your cluster and having a good data model. And lastly, workload prioritization is an enterprise-only feature. So the CQL command presented here will not work in the open source version. Before I take your questions, I would like to let you know about some other Scylla events coming up. So join our next summer Tech Talks, how to bulletproof your Scylla deployment, and another one, incremental compaction on September 4th. Also, join us at Scylla Summit in San Francisco in November. We'll have 2 full days of technical content, networking with Scylla engineers and your peers, plus pre-summit training day. It's a great event and we hope to see you there. So now we'll take your live questions. Use the Q&A feature at the bottom of the console. So I'm asked how will I know how many shares to give each service level? So actually, you don't need to be that strict about it. You only need to make sure that the relation between the tasks that you want to balance is reasonable. For example, if you'd like all of the tasks to get fair share of resources, you just have to give them all the same amount of resources, and it doesn't really matter how many. On the other hand, if you, for example, would like that on the worst case, someone will get only one third of the resources, so you just give him a third of the highest shareholder or the sum of shares that you already gave to someone. And another question, how many workloads can I have? So this is a very good question. This feature is still on a preview. And right now we allow for something like 5 or 6 workloads. It depends on the actual version. But to be on the safe side, I would not use more than 5. Nothing will happen if you do, except that the database will not honor all of the service levels, only the first 5 or 6 ones that were created. Okay, so if no, oh, I have another question. Can I use this feature to distinguish between different OLTP users, for example? Yeah, yes, you can. You actually can. We showed the example with the three loads a few slides before. Maybe I will go back to it and try to show it again. Okay, so this is the exactly what you were looking for. So here you can see that actually what mattered to us was latency, or better yet, the latency that one of the OLTP users gets will be better than the other. If, on the other end, you would like all OLTP users not to affect each other, so you would give each one of them the same amount of shares. This would promise that every one of them will get only third of the cluster when it is loaded, and all of them would like to use all of the resources. And this means that the latency will converge to something reasonable and not, and they will not impact each other for more than 1/3 of the resources. Okay, so if no other questions, so thank everyone for attending. We'll be sending you a recording and the slides. See you at the next webinar. Thank you.